Okay, everyone, this is the chapter 11. This is one section for chapter 11, and it's the end. This is the last section we're going to do. It's kind of a combination of a couple chapters. So we will, in class, have done, I hope, I'm doing this beforehand, some review of lines of best fit, regression, least squares regression line. So at this point, hopefully you remember how to find a least squares regression line, how to look at residuals, how to draw a residual graph, that sort of thing. So I'm going into today's lesson with that understanding. And what we're going to do is we're going to do confidence interval and hypothesis test for the slope of the line of best fit. Okay. So first things first, there's a new term. We talked about it earlier in the course, but I'm going to bring it up again. It's called R squared. So R squared does have some important ideas in statistics. We don't really study them at all in this class. We just tell you what it means, and then we just kind of go along our merry way and not spend a lot of time with it. And then later on, if you study more statistics, you'll learn a little bit more about it. So R squared is actually called the coefficient of variation. So if anyone actually asks you to find the coefficient of variation, it's a pretty typical question. They're just asking you to find R squared. So you would find R in your calculator and then just square it, yeah? Although, does R squared even show up on your calculator? I don't know. Maybe it does. Real quick, sorry. I guess I should probably know this. We do a little line of regression. Probably should have done this beforehand, sorry. Yeah, R squared does show up on the calculator. So I probably should have known that too, sorry. But you can just square R, of course, also. There's some math behind it. R squared is actually the explained variation in X over the total variation. So in other words, this is the way you say it. Let's say R squared happened to be 83.4%, which I think it might be for the data I have here, but don't worry about that. So that 83.4% means 83.4% of the variation in the sales, which is our Y variable in this case, can be explained by the variation in advertising. So forget about sales and advertising because I didn't do the examples, just Y and X. Okay, the leftover is unexplained. So there's a connection between the two is the idea, but then there's other stuff going on also. And so the connection between the two is what R squared is. So it's the variation in the sales that can, or in the Y variable that can be explained by the variation in the X variable. Okay, so it's just a term that you need to know. Basically, the way a question would be asked is find the coefficient of variation. Or they might say, what percent of the data in the variation in sales can be explained by the variation in advertising? In either case, they're asking for R squared. All right, so what we're going to do is, some terminology, first of all, sorry. Real quickly, some terms. When you do a prediction, so you predict your Y value from your X point. It's called a prediction. It's called a point estimate. So they will be off the real values, right? Those are called the residuals. So we have this thing that's actually called the standard error of those point estimates. It's like on average, how far away from the line are they? Okay, this is called S. S has a formula attached to it. It's on your note sheet. You don't need to know the formula. I'm just telling you how it's figured out. You can see how much Y is changing from the Y, which is the idea there. We're going to wind up doing a line of regression t-test. S is one of the numbers. I'm not going to show you on the calculator on this video. We'll show you in class, or you can just follow along just by doing a line of regression t-test. It's on there. So one of the data things that pops out there, and it gives you the test statistic, gives you the p-value. It also gives you S. It just tells you what that is. Then there's another term that's called the standard error of the slope. We're going to need the standard error of the slope when we do the confidence intervals, because if you think about a confidence interval, actually we're going to need to find the test statistic also, because all our test statistics or confidence intervals are using the standard error, right? And every summary statistic, mean, proportion, has its own standard error. So does this one. There's a formula attached to this one. Okay, you don't need to know this formula. Again, that standard error is going to pop up for us. Not a big deal. It's either going to be given to us in like a computer printout or just told to us in the problem if we need it. Okay. So we have two things: hypothesis test for slope, and then confidence interval for slope with some interpretation. So I'm just going to walk you through it. No examples today, I don't think. Hopefully a generic idea will be enough for you. Oops, information right there, sorry. So here we go. So what is a hypothesis test for slope? Well, the idea is we want to understand if there's some meaningful relationship, right? So we've used like correlation before, like 0.8 is a pretty high correlation. But how high is high enough? Is there really a relationship between these two things that the line of best fit? You can find a line of best fit for any data points, but is there really a relationship? So the idea is if the slope was 0 of the line of best fit, there would be no relationship. It just means it's all over the place. So the hypothesis test is actually going to test for the relationship by testing whether or not the slope is 0. So it's for determining that the non-zero correlation or slope, because if correlation is 0, slope will be 0 also, didn't happen by chance. Or in other words, there is some true linear relationship with a non-zero slope, and knowing the value of x is actually helpful in predicting the value of y. If there's no relationship that's meaningful, it doesn't matter. So our null hypothesis is just going to be the slope is 0. Or another way to write that is, I'll come down here, linear relationship between whatever the variables are in the problem. Okay, so they mean the same thing. The alternate hypothesis is always, there's no two tail or less, one tail really, we don't really worry about greater than or less than, we just worry about is it 0 or not 0. So the alternate is not 0, meaning there is a linear relationship. Whoops, sorry, I put no, whoa, I messed that up. Sorry, let me come back here. That should have been no linear relationship, right? If the slope is 0, there is no linear relationship. But if the slope is not 0, then there is a linear relationship. So if you reject the null hypothesis, you would accept the fact that there is a linear relationship. The test statistic is found the same way it's always found. It's the actual value, what we got, which is our real slope. So we would do a line of best fit, right? You'd put list 1, list 2, find the line of best fit, find the slope, and then subtract what we expected to get, which is always 0, and then divide it by the standard error. For the most part, you're just going to do this on your calculator, so you're not going to need those numbers. You just hit the line of regression t-test on your calculator. It's going to give you that number. However, sometimes we get computer printouts that have this information in it for us, and then we would need to use this formula. So the formula still becomes important. B1 is the slope, right? It's the estimate from the samples, just to remember. This is a t-distribution, so it has degrees of freedom. And this one, it actually has n-2 degrees of freedom. This one's a little bit different than the ones from the actual t-distributions where it was n-1. So when you're doing a problem, I'm not actually going to do a problem. You're going to go through the steps. So it has conditions. The conditions are it needs to either be a simple random sample or an experiment. So often these numbers come from experiments, science, that sort of thing. So it's not really a simple random sample. So if it's an experiment, you can just say this was a good experiment. The only other condition is that a line seems like a good fit. So what we need to do is for every one of these problems in our conditions, we need to draw a residual plot. Okay, hopefully we will have reviewed that in class. I'm not going to review it right now. So you're actually going to have to draw that residual plot on your paper, so you can be kind of rough about it. So let's just say the residual plot, I don't know, we'll just kind of, the idea is remember that a random residual plot. Okay, so I would say no pattern in residuals. Remember that a random residual plot implies the line is a good fit. If there's a pattern, then we wouldn't want to try this. We'd probably say, no, this is probably not a line. Let's go into something else. Okay, no pattern residuals, so line probably a good fit. This is what you would write for your condition. Okay, draw the actual picture. Do it on your calculator. But then draw the picture on the paper and then say there's no pattern residuals. Don't try to find a pattern. None of these problems are meant to have a pattern in them. They're all meant to be done, so just do it. And then you would just go through your normal steps, right? Null hypothesis, slope is 0. Alternate, slope is not 0. Okay, you would find your t stars with n-2 degrees of freedom. Then you run the test, line of regression t-test on your calculator, or using the formula, you get a t-test statistic, you get a p-value, and then you come up with your conclusion. So I'm not going to do an example because we've done enough of these. It's all going to work the same, okay? And then the last thing is just the confidence interval for the slope. It's built exactly the same way all our other confidence intervals are built. what we got, B1 plus or minus the critical value, T star with n minus 2 degrees of freedom, same one from before, times that standard error of the slope formula. So either you're going to be given that form or given that number from like a computer printout. So once you're given that number, you can just use it. Or you're just going to do this on your calculator. This is a linear regression T interval. Okay, so you're not going to have to use that formula that I gave you back at the beginning for that. So that's it. We'll talk about the, actually, let me talk about the wording right now. So the wording would be, I'm going to shorthand this. I am 95% sure. Now, you can't say, so this is a slope, right? So we're going to get a number. So maybe the slope's between 4 and 6. You can't say I'm 90% sure that the slope is between 4 and 6. You also have to talk about what slope means. So you kind of have to interpret slope in there also. So you would say, I am 95% sure that for each increase in 1 unit of x, so we're thinking slope now, right? Y over x. There is an increase or decrease, if it's negative, somewhere between whatever the slope is. In this case, I'd set 4 and 6 units in y. So notice I'm using the interpretation of the confidence interval, and I'm also using the interpretation of the slope in there. So we'll talk about that a little bit more in class also. And just one last little thing, there is a connection. If you think about the test statistic, if we go back to the test statistic is what we got minus what we expected to get, which is 0, over the standard error, whoops, that should have been B1, which is 0, over the standard error of the slope. You can manipulate this formula, and you can get the standard error from other ways. So the point of this is sometimes they're going to give you awkward information. Like they might just tell you the test statistic and ask you to find the standard error to be able to use it in this formula or something like that. You'll see a homework problem where there's a computer printout that helps you with this. So there's just know that there's a relationship between the standard error of the slope and the test statistic, which is a lot better than having to use this kind of ugly formula right here, right? Never going to have to use that formula. It is on the note sheet, but you're never going to have to use it. So that's it for chapter 11. I guess congratulations are in order. We just finished statistics, but we still will catch up and do a lot more review. So we'll see you in class.